Well, welcome back to our course, Computer Organization and Architecture. Last lecture, we talked about internal memory. This lecture, we're going to be talking about external memory. And just for context, to give you a reminder, we're going to the second major section in our text about computer systems, and we're talking about a lot of different types of memory. And so this will be the last in series that's going to be focusing on a key part of the computer system and how memory impacts that. So let's go ahead and get into the details of what we're going to cover. First, doing a table of contents or summary, and then at the very end, we'll come back to the same chart. So in terms of external memory, we're going to be talking about three different types: magnetic disk. And so chances are you still have some type of a magnetic style disk, hard disk drive in your home, but this is tending to be a technology that's starting to go by the wayside. We'll be talking about the various ways of how it functions. We'll talk about solid state drives, and we mentioned it briefly in the last lecture, and so we'll get into more details about that, including some practical issues. And then we'll have a little bit of a historical point of view of a magnetic tape. And so you'll get a little bit of a better sense of that. We'll talk about RAID. And so there's a RAID level 0 all the way up to RAID level 6. And so that stands for a redundant array of independent disks. And so each one of them has a slightly different way of doing it. And so if you've ever set up a server, maybe you've encountered this, or a media device where you're trying to have a little bit higher integrity rather than just using one disk. And then finally, we'll talk about optical memory, CDs. That would be the thing that really started this. And I can remember where cassette tapes went out, and this is where CDs came in, and then CDs moved to DVDs, and then DVDs to Blu-rays. And so we'll get a chance to be thinking about that. So let's go ahead and get into one at a time. We'll start out with magnetic disks. So a disk is a circular platter constructed of non-magnetic material called the substrate material, coated with a magnetizable material. Traditionally, the substrate has been an aluminum or aluminum alloy material. More recently, glass substrates have been introduced. The glass substrate has a number of benefits, including the following. It provides for improvement in the uniformity of a magnetic film surface to increase disk reliability. It has a significant reduction in overall surface defects to help reduce read and write errors, and it has the ability to support lower fly levels. So that's going to be described later. We'll have head that reads the things from these platters, and so that's what they're talking about. And has better stiffness to reduce disk dynamics and greater ability to withstand shock and damage. So now let's think about the magnetic read and write mechanism. We'll give some overview here, and we'll have a couple of diagrams that show you some of the elements they had in the actual platter and how we actually put data onto those platters. Data are recorded on it and later retrieved from the disk via a conducting coil named the head. In many systems, there are two heads, a read head and a write head. During a read or write operation, the head is stationary while the platter rotates beneath it. Maybe you've had an experience where, especially if you have an older hard drive, that maybe it starts to make a little humming noise. And that's when you can actually hear that the platters are rotating. So the write mechanism exploits the fact that electricity flows through a coil, producing a magnetic field. Electric pulses are sent to the write head, and the resulting magnetic patterns are recorded on the surface below with different patterns for positive and negative currents. The write head itself is made of easily magnetizable material and is in the shape of a rectangular donut with a gap along one side and a few turns of conducting wire along the opposite side. And so we'll see that in the next chart in figure 7.1. An electric current in the wire induces a magnetic field across the gap, which in turn magnetizes a small area of the recording medium. reversing the direction of the current reverses the direction of the magnetation on the recording medium. The traditional reed mechanism exploits the fact that the magnetic field moving relative to a coil produces an electric current in the coil where the surface of the disc passes under the head. It generates a current of the same polarity of the one already recorded. The structure of the heads for reading is in this case essentially the same as for the writing, and therefore the same head can be used for both. Such single heads are used in floppy disk systems and in older rigid disk systems. So maybe you've heard of floppy disks. It's sort of an antiquated technology that maybe you've heard of. Maybe you might even still have a floppy disk somewhere. So contemporary rigid disk systems use a different reed mechanism requiring a separate head, reed head positioned for convenience close to the right head. The reed head consists of a partially shielded magno-resistive MR sensor. The MR material has an electrical resistance that depends on the direction of the magnetation of the medium moving under it. By passing a current through the MR sensor, resistance changes are detected as voltage signals. The MR design allows higher frequency operation, which equates to greater storage densities and operating speeds. Okay, continuing on, here is an illustration of what an inductive right magno-resistive reed head. And so here is they refer to as a donut, and you can see there's a little gap below that. And so you can see how that would be laid out. And so this is the thing that rides on top of the platter. And so this next chart gives you an illustration of what the platter looks like. And then we'll next talk about how you actually encode data on it. So the head is a relatively small device capable of reading from or writing to a portion of the platter rotating beneath it. This gives rise to the organization of data on the platter in a concentric set of rings called tracks. Each track is the same width as the head. There are thousands of tracks per surface. And so here in figure 7.2, it depicts the data layout. Adjacent tracks are separated by inter-track gaps. This prevents or at least minimizes errors due to misalignment of the head or simply interference of magnetic fields. Data are transferred to and from the disk in sectors. There are typically hundreds of sectors per track, and these may be of either fixed or variable length. In most contemporary systems, fixed length sectors are used to avoid imposing unreasonable precision requirements on the system. Adjacent sectors are separated by an intersector gap. So we're starting to see some of that laid out here. Let's go ahead and move on. Now let's think about the disk layout methods and how we actually apply the data. And so we have tracks, we have sectors, we have zones. So a bit near the center of the rotating disk travels past a fixed point, such as a reed right head, slower than a bit on the outside. Therefore, some way must be found to compensate for the variation in speed so that the head can read all the bits at the same rate. This can be done by defining a variable spacing between bits of information recorded in locations on the disk in a way that the outermost tracks have sectors with bigger spacing. The information can then be scanned at the same rate by rotating the disk at a fixed speed, known as the constant angular velocity, CAV. Figure 7.3a shows the layout of the disk using CAV. The disk is divided into a number of pie-shaped sectors and into series of connecting tracks. And so here is a sector, there's a piece of the pie, and each one of these layers, we see these little lines that is trying to show you the tracks. The advantage of using CAV is that the individual blocks of data can be directly addressed by tracks and sectors. To move the head from its current location to a specific address, it only takes a a short movement of the head to a specific track and a short wait for the proper sector to spin under the head. The disadvantage of CAV is that the amount of data that can be stored on the long outer track is the same as what can be stored on the short inner track. Because of the density in bits per linear inch, increases in moving from the outermost track to the innermost track. Disk storage capability is straightforward. CAV systems is limited by the maximum recording density that can be achieved on the innermost track. To maximize storage capability, more capacity, it would be preferable to have the same linear bit density on each track. This will require an unacceptably complex circuitry. Modern hard drive systems use a simpler technique which approximates equal bit density per track, known as the multiple zone records, in which the surface is divided into a number of concentric zones. 16 is typical. Each zone contains a number of contiguous tracks, typically in the thousands. Within a zone, the number of bits per track is constant. Zones farther from the center contains more bits, more sectors than the zones closer to the center. Zones are defined in such a way that the linear bit density is approximately the same on the tracks of all of the disk. MZR allows for greater overall storage capacity at the expense of somewhat more complex circuitry. As the disk head moves from one zone to another, the length that is along the track of individual bit changes, causing a change in the timing for reads and writes. Figure 7.3b is a simplified MZR layout with 15 tracks organized into 5 zones. And so we have the tracks and sectors that we already mentioned, and how now we have the zones where it's equating that the amount of time to read each one of those is the same as we go from one track to another, from one zone to another. So it shows 15 tracks organized into 5 zones. The innermost 2 zones have 2 tracks each, with each track having 9 sectors. The next zone has 3 tracks each with 12 sectors, and the outermost 2 zones have 4 tracks each with tracks having 16 sectors. Some means is needed to locate sector positions within a track. Clearly, there must be some starting point on the track and a way of identifying the start and end of each sector. These requirements are handled by means of controlled data records on the disk. Thus, the disk is formatted with some extra data used only by the disk drive and not accessible to the user. So there's some overhead that needs to be allowed for. Figure 7.4 shows 2 common sector formats used in contemporary hard disk drives. The standard format uses many years, divided the track into sectors, each containing 512 bytes of data. Each sector also included control information useful to the disk controller. The structure of the sector laid out for this format consists of the following. There's a gap, so it separates the sectors. There's a sync. It indicates the beginning of the sector and provides timing alignment. There's the address mark. It contains data to identify the sector's number and location, and it also provides status about the sector itself. Then there's data, 512 bytes of user data, and then there's an error correcting code. We mentioned this in previous when we were talking about memory. It's always a good idea to have error correcting code. So it's used to correct the data that might be damaged in the reading and writing process. Although this format has served the industry well for many years, it has become increasingly inadequate for 2 reasons. Applications common in many modern computing systems use much greater amounts of data and manage the data in larger blocks. Compared to these requirements, the small blocks of traditional sector formatting devote a considerable fraction of each sector to control information. The overhead consists of 65 bytes, yielding a format efficiency of 512 over 512 plus 65, so it gives about an 88% efficiency. Second, bit density on disk drives has increased substantially so that each sector consumes less physical space. Accordingly, a media device, a media defect or other error source can damage a higher percentage of the total payload, requiring more error correcting strength. Accordingly, the industry has responded by standardizing a new format for a 496 byte block illustrated in 7.4b, and so that's what we're seeing down here. The data block is a lot larger. The leading head remains at 15 bytes, and the ECC is expanded to 100 bytes, yielding a format efficiency of 496 divided by 496 plus 115, which gives an overall efficiency of 97%, almost a 10% improvement in efficiency. More significant doubling the ECC to 100 bytes enables a correction of longer sequence of bit errors. So here in table 7.1, it lists the major characteristics that differentiate among the various types of magnetic disks: the head motion, the disk portability, the sides, the platters, the head mechanism, and there's more things beyond that. You can feel free to pause the video and look over that in more detail. Let's now talk about the characteristics. First, the head may either be fixed or movable with respect to the radial direction of the platter. In a fixed head disk, there is one read-write head per track. All of the heads are mounted on a rigid arm that extends across all tracks. Such systems are rare today. In a movable head disk, there is only one read-write head. Again, the head is mounted on the arm. Because the head must be able to position above any track, the arm can be extended or retracted for this purpose. The disk itself is mounted on a disk drive, which consists of an arm, a spindle that rotates the disk, and the electronics needed for input and output of binary data. A non-removable disk is permanently mounted in the disk drive. The hard disk is in a personal computer is a non-removable disk. The removable disk can be removed or replaced by another disk. The advantage of the latter type is that unlimited amounts of data are available with a limited number of disk systems. Furthermore, such a disk may be movable from one computer system to another. Floppy disk and zip cartridges disks are examples of removable disks. Maybe you've heard one or both of those types, but those are getting fairly dated at this point. For most disks, a magnetizable coating is applied to both sides of the platter, which then is referred to double-sided. Some less expensive disk systems use single-sided disks. Some disk drives accommodate multiple platters stacking vertically a fraction of an inch apart. Multiple arms are provided, and so that was in figure 7.2. We'll also get a chance to see a little bit more of this as we move forward. Multiple platter disks employ a movable head with one read-write head per platter surface. All of the heads are mechanically fixed, so all at all are at the same distance from the center of the disk and move together. Thus, at any time, all of the heads are positioned over tracks that are of equal distance from the center of the disk. The set of all of the tracks in the platter, all of the same relative, the set of all the tracks in the same relative position on the platter is referred to as a cylinder. And so this is illustrated in figure 7.2. So now let's talk about disk classification. Finally, the head mechanism provides a classification of disk into three types. Traditionally, the read-write head has been positioned at a fixed distance above the platter, allowing an air gap. At the other extreme is a head mechanism that actually comes into physical contact into the medium during a read or write operation. This mechanism is used with a floppy disk, which is a small flexible platter and the least expensive type of disk. And I've already mentioned that. To understand the third type of disk, we need to comment on the relationship between the data density and the size of the air gap. The head must generate or sense an electromagnetic field of sufficient magnitude to write or read properly. The narrower the head is, the closer it must be to the platter surface to function. A narrow head means narrow tracks and therefore greater data density, which is desirable. However, the closer the head is to the disk, the greater the risk of error from impurities or imperfection. To push the technology further, the Winchester disk was developed. Winchester heads are used in sealed drive assemblies that are almost free of contaminants. They are designed to operate closer to the disk and this surface that conventional rigid disk heads, thus allowing greater data density. The head is actually an aerodynamic foil that rests lightly on the platter surface when the disk is motionless. The air pressure generated by a spinning disk is enough to make the foil rise above the surface. A resulting non-contact system can be engineered to use a narrow head that operates closer to the platter surface than conventional wrist disk heads. And most recently, the hard drive that I got for a server that I have was actually a sealed device that actually was using an inert gas. And so it tries to prevent contaminants to enter into it. And so that's an example of what we're seeing with a Winchester head. So next, let's talk about the timing of the disk I/O transfer. The actual details of the I/O operation depends on the computer system, the operating system, and the nature of the I/O channel and the disk controller hardware. The general timing diagram of disk I/O transfer is shown in figure 7.5, and we can see all of these things that need to take place. And so as in each of these devices, in memory, we'll be seeing this in these different types of physical devices for hard drives. We'll see it in different types of processors. There's a lot more underneath the hood than what we typically think about that needs to be considered. When the disk drive is operating, the disk is rotating at constant speed. To read or write, the head must be positioned at the desired track and at the beginning of the desired sector on that track. Track selection involves moving the head in a movable head system or electronically selecting one head on a fixed head system. On a movable head system, the time it takes to position the head at the track is known as the seek time, TS. And so we're setting up all these different parameters that will be needed when we start to be looking at different types of time. In either case, once the track is selected, the disk controller waits until the appropriate sector rotates to line up with the head. The time it takes for the beginning of the sector to reach the head is known as a rotation delay or latency time, the TL. Once the head is at the position, the read or write operation is then performed as the sector moves under the head. This is the data transfer portion of the operation. The time required for the transfer is the transfer time, T sub capital T. The sum of the seek time, if any, the latency time and the transfer time equals the block access time, or simply T sub B, or simply access time. In addition to the access time and transfer time, there are several queuing delays normally associated with a disk I/O operation. When a process issues an I/O request, it must first wait in a queue for the device to be available. At that time, the device is assigned to the process. If the device shares a single I/O channel or a set of I/O channels with other disk drives, then there may be an additional wait for the channel to be available. At that point, the seek is performed to begin disk access. In some high-end systems for servers, a technique known as rotational position sensing is used. This works as follows. When the seek command has been issued, the channel is released to handle other I/O operations. When the seek is completed, the device determines when the data will rotate under the head. As the sector approaches the head, then the device the device tries to reestablish the communication path back to the host. If either the control unit or the channel is busy with another I/O, then the connection attempts fails, and the device must rotate one whole revolution before it can attempt to reconnect, which is called an RPS miss. This is an extra delay element that must be added to the access time. Seek time is the time required to move the disk arm to the required track. It turns out that this is difficult quantity to pin down. The seek time consists of two key components: the initial startup time and the time taken to traverse the tracks that have to be crossed once the access arm is up to speed. Unfortunately, the travel time is not a linear function of the number of tracks, but includes a settling time, the time that is the time after positioning the head over the target track until the track identification is confirmed. A mean time of TS is typically provided by the manufacturer. Much improvements come from smaller and tighter disk components. Some years ago, a typical disk was 14 inches or 36 centimeters in diameter, whereas the most common size today is 3.5 inch, reducing the distance that the arm has to travel. A typical average seek time on contemporary hard drives is under 10 milliseconds. And for laptop hard drives, there's a 2.5 inch standard as well. But those are some things that are out there. Disk, other than floppy disks, rotate at speeds ranging from 36 RPM, 3600 RPM for handheld devices such as digital cameras, up to, as of this writing, 20,000 RPM. At the later speed, there is one revolution per 3 milliseconds. Thus, on average, the latency time T sub L will be 1.5 milliseconds. It is clear that the order in which the sectors are read from the disk has a tremendous effect on the I/O performance. In the case of the access in which multiple sectors are read or written, we have some control over the way in which sectors of data are deployed. However, even in a case of file access in a multi-programming environment, there will be I/O requests competing for the same disk. Thus, it is worthwhile to examine ways in which the performance of disk I/O can be improved over that achieved with purely random access to the disk. This leads to a consideration of disk scheduling algorithms, which is the province of the operating system and beyond the scope of what we're talking about in this lecture and in this book and in this course, but at least we can have a chance to mention it here. Well, let's look at a couple of different types of hard drives to give a sense. And so ranging from an enterprise, a data center, and a laptop application. And so this table gives a disk comparisons for three. The HGST Ultrastar HE is intended for enterprise applications such as the use in servers and workstations. Then we have the HSGS Ultrastar, the C15K600 is designed for use in high performance computing and mission critical data centers installations, so slightly different application. And then we have the Toshiba L200 is an internal laptop hard drive disk. And so you can see the relative size going from 12 terabytes, 600 gigabytes to 500 gigabytes. We can make some useful observations on this table. The seek time depends on part of the power and quantity of the ARM actuator. On the other end of the spectrum, a laptop disk needs to be small, inexpensive, and low power, so the attainable seek time is much greater. Seek time also depends on the physical characteristics. And so for the data center one, the Ultrasena C15K600 has a smaller diameter than the Ultrastar HE. With less average distance to travel, the C15K600 achieves lower seek time. In addition, the C15K600 has a lower bit density on the disk surface, so that the less precision is needed in positioning the read-write head, again contributing to lower seek time. Of course, the penalty of achieving these lower seek times is a much lower disk capacity, going from 12 terabytes down to 600 gigabytes. The Ultrastar C16 Ch07 is likely to be used in applications that call for a high rate of access to the disk, so it is reasonable to invest in minimizing the seek time. Note that the two HGST disks, the average seek time is less for the reads than the writes. And so this is something that is useful to be mindful about, that maybe that when you get into hardware, otherwise you wouldn't notice. For writes, more precision is required to place the write heads dead center on the track. Less precision is needed simply to sense the data that is already there. For the block size or bytes per physical sector, the two HGST disks can be configured for 512 or 4096 bytes. We already talked about that. There's two ways of how you can put data onto the disk. And the laptop disk is offered only for 4096. As discussed previously, the large block size is more efficient in space and more effective in error correction. All right, next we'll talk about RAID, the redundant array of independent disks. And we'll have a couple of different ways of thinking about this, some summary tables, and then we'll have some more detailed specifics of the focus for each one. With the use of multiple disks, there's a wide variety of ways in which data can be organized and in which redundancy can be added to improve reliability. This could make it difficult to develop database schemes that are usable on a number of platforms and operating systems. Fortunately, industry has agreed upon a standardized scheme for multiple disk database design known as RAID, like I said, redundant array of independent disks. The RAID scheme consists of 7 layers, 0 through 6. These layers do not imply a hierarchical relationship, but designate different design architectures that share 3 common characteristics that we have listed here. RAID is a set of physical disk drives viewed by the operating system as a single logical drive. 2, data are distributed across the physical drives of an array in a scheme known as striping, which will be described subsequently. 3, redundant disk capacity is used to store parity information, which guarantees data recoverability in case of a disk failure. The details of the second and third characteristics differ for the different RAID levels. RAID 0 and RAID 1 do not support the third characteristic. The term RAID was originally coined in a paper by a group of researchers at the University of California, Berkeley. The paper outlined various RAID configuration and application and introduced the definitions of the RAID levels that are still used today. The RAID strategy employs multiple disk drives and distributes data in such a way as to enable simultaneous access to data from multiple drives, thereby improving I/O performance and allowing easier incremental increase in capacity. So here is a summary table for each of these 7 RAID levels. And so you can pause the video and read over this in detail, but also give some other information here. The unique contribution of the RAID proposal is to address effectively the need for redundancy. Although allowing multiple heads and actuators to operate simultaneously achieves higher I/O and transfer rate, the use of multiple devices increases the probability of failure. To compensate for this decreased reliability, and so that's what RAID is trying to do, is increase reliability, RAID makes use of stored parity information that enables the recovery of data lost due to a disk failure. We now examine each of the RAID levels as we're showing in this table. It provides a rough guide to the 7 levels to the table. I/O performance is shown both in terms of data transfer capacity or ability to move data, and I/O request rate or ability to satisfy I/O requests. Since each RAID level inherently performs differently relative to these two metrics. Each RAID level storage point is highlighted by darker shading. And so those are some interesting things to be thinking about. Okay, this is the first part of figure 7.6, which illustrates the use of 7 RAID schemes to support data. Data capacity requiring 4 disks with no redundancy. The figure highlights the layers, the layout of user data and redundant data, and indicates a relative storage requirement of the various levels. We refer to these figures throughout the following discussion. Of the 7 RAID levels described, only 4 are common: levels 1, 0, 1, 5, and 6. 0, 1, 5, and 6. And so I'm just going to skip through the second part of this figure so we can see RAID 0, non-redundant; RAID 1, it's mirrored; RAID 2, redundancy through Hamming code; and then we have RAID 3, and they have bit interleaved parity; RAID 4, block level parity; and then once again, for ones that are commonly used, we RAID 5, block level distributed parity; and RAID 6, dual redundancy. So continuing on, now we can be thinking about some of these details. RAID about the data mapping for a RAID level 0 array. And then we'll have some summary charts for each of these levels. And you can be thinking about that as, say, if you're considering the future that you're setting up a RAID, which one you should use, or maybe you have to be using it and you want to be aware of what you gain from the type of RAID that is implemented. RAID level 0 is not a true member of the RAID family because it does not include redundancy to improve performance. However, there are a few applications, such as some supercomputers, in which performance and capacity are primary concerns, and low cost is more important than improved reliability. For RAID 0, the user and system data are distributed across all of the disks in the array. This has a notable advantage over the use of a single large disk. If 2 different I/O requests are pending for 2 different blocks of data, then there's a good chance that the request blocks are on different disks. Thus, the 2 requests can be issued in parallel, reducing the I/O queue time. But RAID 0 has, RAID 0, as with all of the RAID levels, goes further than simply distributing the data across a disk array. The data are striped across the available disks. This is best understood by considering figure 7.7. All of the user and system data are viewed as being stored on a logical disk. The logical disk is divided into strips. These strips may be physical blocks, sectors, or some other unit. The strips are mapped round robin to a consecutive physical disk in the RAID array, a set of logically consecutive strips that map exactly one strip to each array member is referred to as a stripe. In an n disk array, the first n logical stripes are physically stored on the first stripe on each of the n drives, forming the first stripe. The second n stripes are distributed on the second stripes on each disk, and so on. The advantage of this layout is a single I/O request consists of multiple logically contiguous strips. Then up to n strips for that request can be handled in parallel, greatly reducing the I/O transfer time. Figure 7.7 also indicates the use of array management software to map between logical and physical drive space. This software may execute either in the disk subsystem or a host computer. So here we see the logical drive, and so this is what other parts of the computer see, and this is how it's laid out. And in this case, we have 4 physical drives. Okay, now we'll get into the specifics. The performance of any of the RAID levels depend critically on the request pattern of the host system and on the layout of the data. These issues can be most clearly addressed in RAID 0, where the impact of redundancy does not interfere with the analysis. First, let us consider the use of RAID 0 to achieve a high data rate for applications to experience a high transfer rate, two requirements must be met. First, a high transfer capacity must exist along the entire path between the host memory and the individual disk drives. This includes internal controller buses, host system I/O buses, I/O adapters, and host memory buses. The second requirement is that the application must make I/O requests that drive the disk array efficiently. This requirement is met if the typical request for large amounts of logically contiguous data compared to the size of a strip. In this case, a single I/O request involves a parallel transfer of data from multiple disks, increasing the effective transfer rate compared to a single disk transfer. The transaction-oriented environment, the user is typically more concerned with response time than for transfer rate. For an individual I/O request for small amounts of data, the I/O time is dominated by the motion of the disk heads, that is the seek time, and the movement of the disk, that is the rotational latency. In transactional environments, there may be hundreds of I/O requests per second. A disk array can provide high I/O execution rates by balancing the I/O load across multiple disks. Effective load balancing is achieved only if there are typically multiple I/O requests outstanding. This in turn implies that there are multiple independent applications or single transaction-oriented application that is capable of multiple asynchronous I/O requests. The performance will also be influenced by the stripe size. If the stripe size is relatively large, so that a single I/O request only involves a single disk access, then multiple waiting I/O requests can be handled in parallel, reducing the queuing time for each request. So that's for RAID 0. And now we'll, in a quicker fashion, we'll just go through the other levels. And so for RAID 1, it differs from RAID levels 2 through 6 in the way in which the redundancy is achieved. The redundancy is achieved by a simple expedient of duplicating all the data. So data striping is used, but each logical stripe is mapped to two separate physical disks so that every disk in the array has a mirror data containing the same data. RAID 1 can also be implemented without data striping, although this is less common. In terms of the positive aspects, a read request can be serviced by either of the two disks that contain the request data. There is no write penalty. Recovery from a failure is simple. When a drive fails, the data can be accessed from the second one. It provides real-time copy of all data. It can achieve high I/O requests if the bulk of the requests are reads. The principal disadvantage is the cost. Okay, 0 and 1 are common. The next handful aren't so common. So characteristics, it makes use of a parallel access technique. If a parallel access array of all members disks participate in the execution of every I/O request, spindles of the individual drives are synchronized so that each disk head is in the same position on each disk at any given time. So there's going to be a lot of timing things involved here. Data striping is used. Stripes are very small, often as small as a single byte or word. For performance, an error correcting code is calculated across corresponding bits on each data disk, and the bits of the codes are stored in the corresponding bit positions on multiple parity disks. Typically, a Hamming code is used, which is able to correct single bit errors and detect double bit errors. The number of redundant disks is proportional to the log of the number of data disks, and it would be an effective choice in an environment in which many disks have errors. Level 3 requires only a single redundant disk, no matter how large the disk array, employs parallel access with data distributed in small strips. Instead of an error correcting code, a simple parity bit is computed for the set of individual bits in the same position on all of the data disks. It can achieve very high transfer rates. In terms of performance, the event of a drive failure, the parity drive is accessed and data is reconstructed from the remaining devices. Once the failed drive is replaced, the missing data can be restored on the new drive and operation resumed. In the event of a disk failure, all the data are still available in what is referred to as a reduced mode. Returning to full operation requires that the failed disk to be replaced and the entire contents of the failed disk to be regenerated on the new disk. In a transaction-oriented environment, performance suffers. So there's pros and cons. Now for level 4, it makes use of an independent access technique. So these are the characteristics. As an independent access array, each member disk operates independently so that the separate I/O requests can be satisfied in parallel. Data striping is used, so stripes are relatively large, and to calculate the new parity, the array management software must read the old user stripe and the old parity stripe. In terms of performance, it involves a write penalty when an I/O write request of small size is performed. Each time a write occurs, the array management software must update not only the user data, but also the corresponding bit parity bits. Thus, each stripe write involves 2 reads and 2 writes. Okay, let's finish up with these last 2 RAID levels, the level 5 and the level 6. Remember, RAID 0 and 1 and 5 and 6 are commonly used. So for RAID 5, a characteristic that's organized in a similar fashion to RAID 4. The difference is distribution of the parity stripe across all disks. A typical allocation is a round-robin scheme. The distribution of parity stripes across all drives avoid a potential I/O bottleneck found in RAID 4. For characteristics, the 2 different parity calculations are carried out and stored in separate blocks on different disks. Advantages is it provides an extremely high data availability. 3 disks would have to fail within the mean time to repair MTTR interval to cause data to be lost. So very high data availability. It incurs a substantial write penalty because each write affects 2 parity blocks. So here we saw the differences for the level 5 and then the level 6. So that's a quick summary of those, and we'll continue on here. We saw those one at a time, and now we have a comparative summary of each of the 7. Since I spent a lot of time talking about the other ones, you can see this later or pause the video, and you have the advantages, disadvantages of an application. And so maybe taking a look at those might be of use to consider if you're thinking about doing a RAID implementation. So video production and editing, that's RAID 0, RAID 1, accounting, payroll. Those are some examples of things where those are popular. And then for 5 and 6, this can be file and application servers for 5, and perfect solution for mission critical applications. So this is like take it to the bank. Don't ever want to lose your data. That would be a good option, but it's going to be expensive. Okay, let's now talk about another type of hard drive. This is the solid state drive. One of the most significant developments in computer architecture in recent years is the increased use of solid state drives in complement to and ever replacing the hard drive disks, the HDDs. So SSDs are replacing HDDs, both as internal and external secondary memory. The term solid state refers to electronic circuitry built with semiconductors. An SSD is a memory device made with solid state components that can be used as a replacement to a hard disk drive. The SSDs now on the market and coming online use NAND flash memory, so which is described in chapter 5. And we have already mentioned that a little bit, so maybe that's starting to refresh your recollection a little bit as we're thinking it now again. So SSDs have the following advantages over HDDs: high performance input and output operating per second. So IOPS, significantly increased performance, IOs subsystems. The durability, it's less susceptible to physical shock and vibration. It has longer lifespans. SSDs are not susceptible to mechanical wear. Has lower power consumptions. SSDs are considerably less when compared to comparable size HDDs. They're quieter and cooler running. Less floor space is required, lower energy costs, and thus it provides for a greener enterprise. There's lower access time and latency rates. It's over 10 times faster than the spinning disk in a hard disk drive. Currently, HDDs enjoy a cost per bit advantage and a capacity advantage, but these differences are shrinking. And every time I do a price check, I see that true again and again. As the cost of the flash-based SSDs have dropped and the performance and bit densities increase, SSDs have become increasingly competitive with HDDs. Table 7.5 shows typical measures of comparisons at the time of this writing. It would be hard at this point to buy a laptop, for example, that had an SSD, unless it's a lower end device. So it's definitely becoming a mainstay for computers. Now let's talk about the solid state drive architecture. We had a chance to talk about this for platters and hard drives. Now we want to be doing at least a shorter review of what it is for SSDs, sorry. So figure 7 illustrates a general view of the common architecture system component associated with the SSD system. On the host system to operating systems invokes file system software to access data on the disk. The file system in turn invokes IO driver software. The IO driver software provides host access to the particular SSD product. The interface components in figure 7.8 that we're showing refers to the physical and electrical interface between the host processor and the SSD peripheral device. If the device is an internal hard drive, a common interface is a PCIe. For external devices, one common interface is USB. In addition to the interface to the host system, the SSD contains the following components: controller, addressing, data buffer and cache, error correcting, flash memory components. So one at a time here, the controller provides the SSD device level interfacing and firmware execution. For addressing, this is the logic that performs of the selection and function across the flash memory components. For the data buffer and cache, this is the high-speed RAM memory components used for speed matching and to increase data throughput. The error correcting, this is the logic for error detecting and correction. We saw this for a couple of different types of hard drives that we have already mentioned. And then the flash memory components, this is the individual NAND flash chips that are used for the actual memory in a solid state drive. So there are two practical issues that are peculiar to solid state drives that are not faced in HDDs. First, SSD's performance has a tendency to slow down as the device is used. To understand the reason for this, you need to know that files are stored on a disk as a set of pages, typically 4 kilobytes in length. These pages are not necessary and indeed not typically stored as a contiguous set of pages on the disk. The reason for this arrangement is explained in our discussion of virtual memory in chapter 9, so stay tuned for that. However, flash memory is accessed in blocks with a typical block size of 512 kilobytes, so that there are typically 128 pages per block. Now consider what must be done to write a page onto flash memory. The entire block must be read from the flash memory and placed in a RAM buffer. Then the appropriate page in the RAM buffer is updated. Before the block can be written back to a flash memory, the entire block of flash memory must be erased. It is not possible to erase just one page of the flash memory. The entire block from the buffer is now written back to the flash memory. Now, when a flash drive is relatively empty and a new file is created, the page of that file are written on the drive contiguously so that one or only a few blocks are affected. However, over time, because of the way virtual memory works, files become fragmented and pages scatter over multiple blocks. As the drive becomes more occupied, there's more fragmentation. So the writing of the new file can affect multiple blocks. Thus, the writing of multiple pages from one block becomes slower. The more fully occupied the disk is, manufacturers have developed a variety of techniques to compensate for this property of flash memory, such as setting aside a substantial portion of the SSD as extra space for write operations. This is called over-provisioning. Then to erase inactive pages during idle times using the used to defragment the disk. Another technique is the trim command, which allows an operating system to inform a solid-state drive SSD which blocks of data are no longer considered in use and can be wiped internally. A second practical issue with flash memory drives is that a flash memory becomes unusable after a certain number of writes. As flash cells are stressed, they lose their ability to record and retain values. A typical limit is 100,000 writes. Techniques for prolonging the life of an SSD drive include front-ending the flash with a cache to delay and group write operations using wear leveling algorithms. This evenly distributes writes across blocks of cells and sophisticated bad block management techniques. In addition, vendors are deploying SSDs in RAID configuration to further reduce the probability of data loss. Most flash devices are also capable of estimating their own remaining lifetime so systems can anticipate failure and take preemptive actions. So there's good there's good and bad about using SSDs, but it definitely seems to be growing in its application. All right, well, the last area that we're going to talk about is the optical disk products. We'll briefly go over tapes storage as well, and let's go ahead and give an idea. And the table that we're showing here is a range of types of devices that are out there. So in 1983, one of the most successful consumer products of all times was to introduce the compact disc, CD, digital audio system. And so instead of having cassette tapes, you can have a CD. The CD is a non-erasable disc that stores more than 60 minutes of audio information on one side. The huge commercial success of CDs enabled the development of low-cost optical disc storage technology that has revolutionized computer data storage. A variety of optical disc systems have been introduced, and we're showing that here, going from the CD all the way to the Blu-ray DVD, and you can have a Blu-ray writer as well. So let's talk about how it works. So both the audio CD and the CD-ROM compact disc read-only memory share a similar technology. The main difference is that the CD-ROM players are more rugged and have error-correcting devices to ensure data are properly transferred from disk to computer. Both types of discs are made the same way. The disc is formed from a resin such as polycarbonate. Digitally recorded information, either music or computer data, is imprinted on a series of microscopic pits on the surface of the polycarbonate. This is done, first of all, with a finely focused high-intensity laser to create a master disc. The master disc, in turn, is used to make a die to stamp out copies onto polycarbonate. The pitted surface is then coated with a highly reflective surface, usually aluminum or gold. The shiny surface is protected against dust and scratches by a top coat of a clear acrylic. Final label can be silkscreen onto the acrylic. So that maybe gives you a little bit of an idea of how it is actually manufactured. Now let's talk about CD operation. Information is retrieved from a CD or CD-ROM by a low-powered laser housed in an optical disc player or drive unit. The laser shines through the clear polycarbonate while a motor spins the disc past it, as we're showing here in figure 7.9. The intensity of the reflected light of the laser changes as it encounters a pit. Specifically, if the laser beam falls on a pit, which has a somewhat rougher surface, the light scatters and a low intensity is reflected back to the source. The area between pits are called lands. A land is a smooth surface which reflects back at higher intensity. The change between pits and lands is detected by a photo sensor and converted into a digital signal. The sensor tests the surface at regular intervals. The beginning or end of a pit represents a 1. Where no change in elevation occurs between intervals, a 0 is recorded. Recall that on a magnetic disk, information is recorded in concentric tracks. With a simple constant angular velocity, the CAV system, the number of bits per track is constant. And an increase in density is achieved through multiple zone recording, in which the surface is divided into a number of zones, with the zones farther from the center containing more bits than zones closer to the center. Although this technique increases capacity, it still is not optimal. To achieve greater capacity, CDs and CD-ROMs do not organize information on a concentric tracks. Instead, the disks contain a single spiral track begins near the center and spins out to the outer edge of the disk. Sectors near the outside of the disc are the same length and thus near the inside. Thus, information is packed evenly across the disc in segments of the same size, and these are scanned at the same rate by rotating the disc at variable speeds. So for a CD, as compared to a hard drive, there is variability in the speed in which it rotates. The pits are then ready by the laser, are read by the laser at a constant linear velocity, CLV. The disc rotates more slowly for access near the outer edge than for those near the center. Thus, the capacity of the track and the rotating delay between the increase for the positions nearer the outer edge of the disc. The data capacity for a CD-ROM is about 680 megabytes. So for the block format, data on the CD-ROM are organized as a sequence of blocks. A typical block format is shown here in figure 710. It consists of the following fields: the sync field identifies the beginning of a block. It consists of a byte of zeros, 10 bytes of all ones, and a byte of all zeros. Then we have the header. The header contains the block address and the mode byte. Mode 0 specifies a blank data field. Mode 1 specifies the use of an error correcting code in 2048 bytes of data. Mode 2 specifies 2336 bytes of user data with no error correcting. There's the data, that's the user data, and there's auxiliary user data in mode 2. In mode 1, this is where the 288 bits of error correcting code is located. With the use of CLV, random access becomes more difficult. Locating a specific address involves moving the head to the general area, adjusting the rotating speed, and reading the address, and then making minor adjustments to find and access the specific sector. So CD-ROM is appropriate for a distribution of a large amount of data to a large number of users. Because the expense of the initial writing process, it is not appropriate for individual applications. Compared with traditional magnetic disks, the CD-ROM has two advantages. The optical disk storage with the information stored in it can be mass replicated inexpensively, unlike a magnetic disk. The database on the magnetic disk has to be reproduced by copying one disk at a time using 2 disk drives. The optical disk is removable, allowing the disk itself to be used for archival purposes. Most magnetic disks are non-removable. The information on non-removable magnetic disks must be copied to another storage medium before the disk drive or disk can be used to store new information. The disadvantage of CD-ROMs are as follows. It is a read-only and cannot be updated. It has an access time much longer than that of a magnetic drive, disk drive, and it can be as long as half a second. Well, now let's talk about some of the other type of things that we listed in our table earlier. We'll talk about the writer, the CD writer or CD recordable, and also the CD rewritable to accommodate applications in which only one or a small number of copies of a set of data is needed. The write once, read many times CD, known as a CD recordable, CDR, has been developed. For a CDR, a disk is prepared in such a way that it can be subsequently written once and only once with a laser beam of modest intensity. Thus, with a somewhat more expensive disk controller than a CD-ROM, the customer can write once as well as to read the disk. The CDR medium is similar to, but not identical to, the CD or CD-ROM. For CDs and CD-ROMs, information is recorded by a pitting of the surface of the medium, which changes reflectivity. For a CDR, the medium includes a dye layout. The dye is used to change reflectivity and is activated by a large intensity laser. The resulting disk can be read on a CDR drive or a CD-ROM drive. The CDR optical drive is attractive for archival purpose of documents and files. It provides a permanent record of large volumes of user data. The CDRW optical disk can be repeatedly written and overwritten, as with a magnetic disk, allowing a number of approaches have been tried. The only pure optical approach that has proved attractive is called phase change. The phase change disk uses a material that has 2 significant different reflectivities in 2 different phase states. There's an amorphous state in which molecules exhibit a random orientation that reflects light poorly, and a crystalline state which has a smooth surface that reflects light well. A beam of laser can change the material from one phase to another. The primary disadvantage of phase change optical disks is that the material eventually and permanently loses its desirable properties. Current materials can be used for between 500,000 and 1 million eraser cycles. The CDRW has the obvious advantages over CD-ROM and CDR, that it can be rewritten and thus used as a true secondary storage. As such, it competes with a magnetic disk, which we'll talk about, which we already spoke about. A key disadvantage of the optical disk is that the engineering tolerances for optical disks are much less severe than for high capacity magnetic disks, that they exhibit high reliability and longer life. Okay, well, let's think about a CD-ROM and a DVD-ROM. With a capacity of digital versatility disk, what a DVD stands for, digital versatility disk, the electronic industry has at its found at its disposal replacement for the analog VHS video tape. The DVD has replaced the videotape in video cassette recorders, VCR, and most importantly for this discussion, replace a CD-ROM in personal computers and servers. The DVD takes video into a digital age. It delivers movies with impressive picture quality, and it can be randomly accessed like an audio CD, which DVD movies can also play. Vast volumes of data can be crammed onto a disk, currently 7 times as much as a CD-ROM. With DVD's huge storage capacities and vivid quality, PC games have become more realistic and educational software incorporates more video. Following in the wake of these developments has been a new crest of traffic over the internet and corporate intranets as the material is incorporated into websites. The DVD's greater capacity is due to 3 differences from CDs. First, bits are packed more closely on a DVD. The spacing between loops of a spiral on a CD is 1.6 microns. And then the minimum distance between pits along the spiral is 0.834 microns. The DVD uses a laser with shorter wavelengths and achieves a loop spacing of 0.74 microns and a minimum distance between pits of 0.4 microns. The result of these 2 improvements is about a 7-fold increase in capacity to about 4.7 gigabytes. Second, the DVD employs a second layer of pits and lands on top of the first layer. A dual layer DVD has a semi-reflective layer on top and a reflective layer. By adjusting the lasers, that the DVD drives can read each layer separately. The technique almost doubles the capacity of the disk to about 8.5 gigabytes. The lower reflectivity of the second layer limits the storage capacity so that a full doubling is not achieved. The DVD-ROM can be two-sided, whereas data are recorded on only one side of a CD. This brings the total capacity up to 17 gigabytes. As with the CD, DVDs come in writable as well as read-only versions. So high definition optical discs are designed to store high definition videos and to provide significant greater storage capability compared to DVDs. The higher bit density is achieved by using a laser with a shorter wavelength in the blue-violet range. The data pits, which constitute the digital ones and zeros, are smaller on the high definition optical disc compared to the DVD because of a shorter wavelengths. 2 competing disc formats and technologies initially competed for the market acceptance, the HD DVD and the Blu-ray DVD. The Blu-ray scheme ultimately achieved market dominance. The HD DVD scheme can store 15 gigabytes on a single layer on a single side. Blu-ray positions the data layer on the disc closer to the laser, which is shown on the right-hand side of each diagram in figure 7.12. What we're showing here on the picture that we're talking about. This enabled a tighter focus, less distortion, and thus smaller pits and tracks. Blu-rays can store 25 gigabytes on a single layer. 3 versions are available: the BD-ROM, the BD-R, the recordable, and the rewritable version, the BD-RE. All right, so we're finishing up now. We just have 3 more charts that we'll be talking about the magnetic tape, a historical source of doing storage, and has some interesting technology in its own right that has been done over time. The tape systems use the same reading and writing techniques as disc systems. The medium is a flexible polyester, similar to what is used in some clothing. The tape is coated with a magnetic material. The coating may consist of particles of pure metal and specialized binders or vapor-plated metal films. The tape and the tape drive are analogous to the home tape recorder system. The tape widths vary from 0.38 centimeters, about 0.15 inches, to 1.27 centimeters, about a half an inch. The tapes used to be packaged on open reels that had to be threaded through a second spindle for use. also called the reel-to-reel. Today, virtually all tapes are housed in cartridges. Data on a tape are structured as a number of parallel tracks running lengthwise. Earlier tape systems typically used 9 tracks. This made it possible to store data 1 byte at a time with an additional parity bit on the 9th track. This was followed by a tape system using 18 or 36 tracks corresponding to digital words or double word. The recording of data in this form is referred to as parallel recording. Most modern systems instead use serial recording, in which data are laid out as a sequence of bits along each track, as done with a magnetic disc. As with the disc, data are read and written in contiguous blocks called physical recording on a tape. Blocks on the tape are separated by a gap referred to as an inner record gaps. As with the disc, the tape is formatted to assist in locating physical records. So the typical recording technique used on serial tapes is referred to as serpentine recording. In this technique, when data are being recorded, the first set of bits is recorded along the whole length of the tape. When the end of the tape is reached, the heads are repositioned to record a new track, and the tape is again recorded on its whole length. The time in the opposite direction, that process continues back and forth until the tape is full. So we're showing how this looks in this figure 7.13. To increase speed, the read-write head is capable of reading and writing a number of adjacent tracks simultaneously, typically 2 to 8 tracks. Data are still recorded serially along individual tracks, but blocks in sequence are stored on adjacent tracks, as is suggested by 7.13b, what we're showing on the bottom of this figure. A tape drive is a sequential access device. If the tape head is positioned at record 1, then to read record N, it is necessary to read physical records 1 through N-1 at a time. If the head is currently positioned beyond the desired record, it is necessary to rewind the tape a certain distance and begin reading forward. Unlike the disc, the tape is a motion only during a read or write operation. In contrast to the tape, the disk drive is referenced to a direct access device. A disk drive need not read all of the sectors on a disk sequentially to get to the desired one. It must only wait for the intervened sectors within the one track and can make successive accesses to any track. Magnetic tape was the first kind of any secondary memory. It is still widely used in lower cost, slowest speed member of the memory hierarchy. And so it still has a place on the table, but it is definitely something that is starting to go away. So the dominant technology today is cartridge system known as linear tape open, LTO. LTO was developed in the late 1990s as an open source alternative to various proprietary systems on the market. And table 7.7 shows the parameters for the various LTO generations. I won't go through that, but you can feel free to look over that at your leisure. So let's just finish up real quickly what we covered. We talked about a variety of different external memories. We talked about magnetic disks. We talked about solid state drives and how they're starting to take over the area that were handled by magnetic disks. We talked about magnetic tapes at the very end, giving a historical view of that. We also talked at the various levels of RAID. Levels 0 and 1 and 5 and 6 are most common. And then we talked about optical memory, compact discs, CDs, DVDs, and Blu-ray drives are the things that we focused on. All right, thank you very much. That ends this lecture. Bye-bye now.